We have now found the acceleration of the two-block system and without using a single number, right? All letters up here. That's the way to solve physics problems. Work out the algebra first and then substitute in the numbers if you were given any numbers. A lot of times the APC questions don't give you numbers, they just want to see the algebra. This has a few other benefits, one of which is your teacher is more apt to give you partial credit if the work is shown. In class, the work is more important than the actual numerical answer. It's only when you start building rockets and bridges that numbers are very important, of course. Another more physical benefit is we can now take limiting cases to both validate the work we did and to observe interesting phenomena. What if the angle theta, right here, was set equal to 0 degrees or 90 degrees? Those are two fairly obvious limiting conditions, right? In one case, you just have a flat situation, and in the other, it's totally vertical. So what would the system look like? Well, I just kind of showed that a little bit. But imagine rotating the incline clockwise, so that's this way. Just keep making it steeper and steeper until the incline is vertical for the 90-degree case, or rotate it counterclockwise, right? You just keep going down like this until the incline is horizontal for the 0-degree case. Start with the 0-degree system. Did you come up with the physical picture for the 0-degree case? If not, we'll be showing it on the next slide. And we'll start with the algebra and just set theta equal to 0. So here's our equation. We substitute 0 in for theta, and we come up with this expression here. m1 minus mu k m2 parentheses times g over m1 plus m2. Is this a familiar equation? As promised, here's the picture. If we set this theta here equal to 0, this guy is being pulled along a flat surface, and then it's not quite the exact picture, but we're going to have m1 falling off this flat surface connected by the pulley. And we've got the case of a block pulling another block off of a table. And what's pulling this down? What's giving us our acceleration? Just this block, which is m1g. And what's the external force holding us back? That's just the friction force on m2, which is mu k m2g. And this should be giving you a hint for how we're going to solve this problem next, where we take the two blocks as one system, because what are we dividing by? The total mass of the two blocks. Time for the 90-degree system. Any luck? And again, don't worry, we'll be showing it on the next slide. But go ahead and start with the algebra, and this time set theta equal to 90 degrees. And there's the 90 degrees. And we come up with this. This may look familiar to you. And again, if not, we'll show it on the next slide. We have no coefficient of kinetic friction because m2 is barely in contact with the rotated incline. Because if we've got the incline like this, and here's m2, the incline is not under m2 at all, so it's just going to slide down here. There's no friction. The incline plane becomes an outwards machine. We've got m1g pulling you down, and then if we made this angle here, we make it theta like this. We've got the block. Up here would be the pulley, and here's the other block. So you have to use a little imagination. And there's no friction here, and you're going to think, well, why not? It's sliding down. Well, it's not really making contact with it, so there's no normal force between these two. He's just moving down in this direction. So no normal force, no friction. So the equation here, m1g is acting to pull the system down and in the direction, and what is that? That's counterclockwise. m2g is trying to make it go clockwise, but it's losing the battle because m1 is bigger, so this is a negative force. And you can see the negative right there. So the limiting cases, well, they do validate our equation. It doesn't mean it's right, of course, but it means at least it's consistent with two limits that we chose.